Hello. So in this lecture, we're going to go through the chemistry of, we're going to be introduced to the chemistry of carboxylic acid derivatives. And so that usually requires a little bit of nomenclature to get us going. So without further ado, we're going to talk about carboxylic acids and their derivatives. Okay, so if we look at the carboxylic acid, we have this framework where we have some R group attached to a carbonyl with an OH attached to it. Now this is called a carboxylic acid because if we look at this hydrogen, maybe I'll not circle that, I'll just say the OH has a pKa of on the order of 1 to 6, and we can get outside of that range if we really need to with a number of tricks. But the point is here, these things are at least slightly acidic, but they can be strongly acidic, slightly to strongly acidic. I guess slightly, a better word for that is weakly, right? We have strong and weak bases and acids. Okay, anyway, neither here nor there. Okay, so that's the carboxylic acid. That's why it has that second word acid attached to it. It is slightly acidic, but that's not all. We have the derivatives of carboxylic acids that we should consider as well. And these include molecules where the OH is converted to some R group. I'm going to label that as an R prime just to indicate it doesn't have to be same on the left or the right. This is called an ester. We'll talk quite a bit about those. We'll make those in lab 10. Oops, I just did that one. The next one is if we have, instead of an OR, we have an O to a carbonyl, which then goes to another R group. That R group could be the same or different. This is an anhydride or a carboxylic acid anhydride. But for the most part, people call these anhydrides. There are molecules where we replace the O with an X group, where X is a halogen. These atoms are fine and iodine is questionable, but this is a little bit too unstable, but this is an acid halide or acyl halide. And often we would, chloride's the most common one of these, and we would call that an acyl chloride or an acid chloride to be specific. Okay, and then the last derivative is one where we replace the nitrogen with an O, or excuse me, the O with a nitrogen, and then we can have groups hanging off the nitrogen. So nitrogen could have R or H. Now this group has a name that's spelled this way, and sort of depending on where you are in the world, this is an amide or an amide. I've heard very important people call it both, and important meaning authority figures in organic chemistry. So amide is what I tend to use, but if you want to go with amide, you would be respected by certain people. And sometimes I worry that by me saying amide, I'm appeasing one group and making another group mad. I don't know. So sometimes I just am like that molecule. I don't know. So it's amide or amide. I think Midwestern, it's a little bit more amide. But anyway, moving away from the overarching kind of names of the functional groups, let's get into some IUPAC naming. So IUPAC naming. Now, I'm most interested in us knowing carboxylic acids and esters. We could certainly spend a lot of time talking about all of the carboxylic acid derivatives, but I just want to focus on the carboxylic acids and the esters. So that's what we're going to go through, and then we're going to call that good for nomenclature on carboxylic acids and their derivatives. Okay, so with carboxylic acids, Carboxylic acids. Let's first of all call out an important and helpful point. C1 is most often the carboxyl group, which, if I say that a little bit more clearly, that's the carbonyl carbon. Okay, so, and that's due to usually that makes the most sense, but in general, that's a priority system. So if we had, let's not get carried away on a carbon count here. Let's have a 5-carbon chain, carboxylic acids drawn on the right, and then on the left, second to the end, I'm going to put 2 methyl groups. And so what this is this is a molecule where the parent chain is 5 carbons long. And we can count any of those methyl groups. So this is a pentane carboxylic acid. Now that's not right. That's not what we would say. I'm just saying it's a carboxylic acid with a pentane parent chain. Instead, we would just call this pentanoic acid. Pentanoic acid. And then we'll put the methyl groups ahead of it, and we'll give those the number 4. Now, I realize that in terms of substituent numbering, if we gave the carboxylic acid carbon, if we numbered that as 5, we would actually get lower numbers overall, seemingly, but we actually kind of hide the carboxylic acid in here. Well, I guess 1, 4, 4, that's 9 versus, oh yeah, 2, 2, 2, 2, 5 is 9. Shoot, I picked one that tied, darn it. Well, the carboxylic acid is going to be number 1 in most cases, and so this is going to be 4, 4 dimethyl pentanoic acid. Now, I'm not going to put the 1 in there. We just kind of assume that there's a 1. What I want to point out is that we have a space here. Okay, so what did we do with the name? We took the ANE suffix, replace the ANE suffix with anoic space acid, anoic acid. Okay, so that kind of covers it. Otherwise, the rules are pretty much the same. It's nice because the carboxylic acid is going to tell you where carbon 1 is. Yeah, okay, now there are some non-IUPAC names that are worth knowing. Let me say it this way. These are IUPAC names, I guess, but they don't follow the traditional IUPAC rules because they're so common. So non-IUPAC common names to know. I should just call this like common names to know. That's what I should do, because these are all IUPAC accepted. Like IUPAC said, hey, these molecules, the common names are so important in history. Let's just go ahead and call them by their common names. So common names to know, okay, that don't follow the traditional rules. We've actually touched on all of these already, but this molecule with a 4-methyl group is a carboxylic acid, and so we would call that a formic acid, okay? So that's a formic acid. Now, a carboxylic acid with an acetyl group is acetic acid. And that's just vinegar, common molecule we see everywhere. Formic acid is the poison that fire ants use. Benzoic acid is another common acid that just has a benzene ring attached to the carboxylic acid. And we've seen that before, so that's benzoic acid. Okay. Now, one thing I want to make sure I touch on fairly early, this is actually pretty important, maybe I should have led with this is a shortcut, sort of shortcut or shorthand for the carboxylic acid group. So what people will often do is they'll, instead of writing R carbonyl OH, they will shorten this to RCO2H. RCO2H. So this is supposed to kind of map onto this group. Now, where it gets confusing to people is the CO2. Now, with CO2, we have the thing on the left is attached to carbon, and the thing on the right is attached to the oxygen as a single bond. So not the carbonyl oxygen, but the other oxygen. So let me show you what I mean by this. So if we take acetic acid, we could shorten this to MECO2H, or instead of Me, we could have CH3CO2H. Okay, so the carboxyl group is shown right here. I'm going to pick a different color because I just had that color. Here is the carboxyl group. Now this says that the methyl is on carbon. And the H is on oxygen. So the methyl is on carbon, the H is on oxygen. Okay, so that's what that shorthand refers to. And that can be really helpful if you have big molecules. But the issue is we have to be aware of the intended connectivities, because if we flip this, we get to different molecules. Flipping the sides gives different molecules. Okay, so if instead I wrote HCO2Me, that's actually an ester. Okay, because what we have here is we have the carbonyl. Now the thing on the right next to the 2 is our methyl group, and the thing on the left is our hydrogen. So this would actually be methyl formate. We should name that later when we talk about ester naming. Okay, so that's not going to work. We can't flip the sides, otherwise we get to different molecules. Okay, so it's kind of important. All right, and you know what that means is if you have a molecule, like this where you've contorted everything, well, let's keep it simple and have like a chain that we can abbreviate there. So if you'll see, we've got an ethyl group and we've got a hydrogen. And so if we try to abbreviate this, we've got our CO2, and then the thing attached to the oxygen is the H, and then a thing attached to the carbon we could abbreviate as ethyl, or we could write it as CH3, CH2, CO2H, or even better, we could just go 2 carbons, CO2H. Where there's my 2 carbons and they're single bonded to that carbonyl oxygen. Okay, that way we can just kind of draw it. We see if you get something really complicated. Speaking of complicated carboxylic acids, let's get into dicarboxylic acids. This isn't something that's super pertinent to the chemistry we're going to be studying in this class. But I find that this naming is really valuable in biochemistry. And that's a big goal of this course, is to set you up to be successful in biochemistry when the reactions that are undergoing have direct consequences for human health and the health of anything that's biological. But the molecules start to get big. They're really just, they're all just made up of the pieces of the functional groups we've been talking about the past 2 semesters in organic chemistry. They're just bigger and they're all connected. And so they're harder to digest in that case. Okay, so dicarboxylic acids. what I'm getting at is if you have a carboxylic acid on a molecule that has another carboxylic acid. Now let's note I could abbreviate this. HO2C, CO2H, because I show the H is attached to the O. I actually kind of flipped it around, the little abbreviation there. But I show my little CH2 bridge between the two. But anyway, this molecule is called malonic acid. It's a dicarboxylic acid, and it's malonic acid. Now that's in contrast to this molecule, which is abbreviated, or even some people write CO2H times 2. But this is oxalic acid. Now, Willoughby, why are you telling me this? Okay, this is this seems to be these names seem to be more and more complicated. Like formic, acetic, benzoic, maybe you bought those because those are functional groups we've kind of talked about before. Dicarboxylic acids we haven't, and we won't. But I want to tell you something that I thought really helped me when I was learning biochemistry, and that's the phrase. Let me spell remember quick. I want you to remember the phrase, oh my, such good apple pie. Okay. And the reason why I want you to remember that is because that has, let me just get this in front of me now. Oops, my battery's about to die. This is palmitic. I thought it was palmitic. Sorry, I'm just checking something. My notes were bad. We'll stop it. I don't have my P right. Okay. Oh my, such good apple pie. Mnemonic for the acids. I just am like losing all of a sudden the P one. I've got it as pickerick. That's not right at all. Pamalic. Okay, we got it now. Okay, so oh my, such good apple pie. What am I talking about here? Well, I want you to focus on the first letters, and these actually are the dicarboxylic. The first letters correspond to the first letter of the dicarboxylic acid names, but in ascending order of carbon count. So O stands for oxalic acid, and that has 2 carbons. Now you can't have less than 2 carbons in a dicarboxylic acid. So there we go. Oxalic acid. And if you look, the structure actually looks like the oxalochloride that we used in the Swern oxidation. That's why I like to know these names, because so many complicated molecules are built from oxalic acid, and then M for my, oh my, such good apple pie, is malonic acid. That's the one we showed earlier. Malonic acid is super important. Now, if you count the carbons, we've got 1 and 2 in oxalic. Now we're at 1, 2, 3 carbons in malonic acid. The last one that I'll draw before I just kind of go through the names. Oh my, such is succinic acid. We're going to be talking about succinic anhydrides and that sort of thing. But succinic acid has 4 carbons. Now at this point, it starts to, hopefully you can start to see the pattern a little bit. We've just got our carbonyl, 1, 2, 3, 4 carbons in this case, if you include the carbonyls, and then the carbonyls are carboxylic acids in either case. So that's succinic acid. Now G is, gosh, okay, I got screwed up here. C is glutaric acid. Sorry, G, glutaric acid. I'm not going to draw that structure. Such good apple is adipic. I had that right. And we could just draw 6 carbons if we needed to. And then P is pamalic. I actually don't draw pamelic acid that much. That's why I forgot what it was. Wait, such good. Yeah, 6 carbons. I don't draw pamelic acid that often, like never. And I only say the word once a year when I'm teaching this class. But this "oh my such good apple pie" really helps me remember oxalic, malonic, and succinic acid, which are hugely important. Then adipic comes in after that with the 6 carbons. You don't see too much of the glutaric acid and the pamelic acid, but it helps with the mnemonic. Okay. So that'll do it for carboxylic acid naming. I want to keep going though and just kind of name esters really quick. It's just a nice one to pick up with. So ester naming, and we want to go back to our abbreviation a little bit, but let's first draw that functional group again. So here's the molecule. Now what we have is we have the carboxy side of the molecule, and then we have the ester side, or alkyl side, I like to say. Now the alkyl, I mean, these both could be alkyl groups, they both could be methyl groups, but that methyl group on the left is inherently baked into a carboxylic acid. And so what we name that, how we name this is we say alkyl space. I'm gonna just write space. I'm not gonna have a line there. Space. And then we're going to name the carboxylate. Okay, now the carboxylate is like the carboxylic acid. So you name it just like the carboxylic acid, except we're going to replace the anoic acid. We're going to cross that out and replace that with anoate. Anoate. Okay, now the alkyl side is just like your alkyl side. This could be methyl, ethyl, whatever it is. Just name it as a substituent, like an ill substituent. Okay, let's go through an example. Okay, so if we look, we've got the carboxy side, which has a 1, 2, 3, 4 carbon parent chain. I'm not going to try to connect the alkyl side and the carboxy side because that oxygen's in the way. So we're just counting the carbons from the carbonyl carbon of the ester to the end of the chain, longest parent chain. So that's 4. So this is a butane chain, which is neither butane nor butanoic acid. It's a butanoate. It's a butanoate. And then on the opposite side with that oxygen, we just have this methyl group here. So the name of this molecule is going to be methyl butanoate. Space butanoate. Okay. Now that substituent on the end could be a little bit more complicated, and the carboxy side could be a little bit more complicated with the addition of extra groups, but we just take each of those sides separately and name them as we would normally. So let's look at this example. So on the carboxy side, 1, 2, 3, 4, 5, and 1, 2, 3. There's our parent chains on both sides of the molecule. So we have, it looks like, oh, I forgot the carbonyls. Shoot, 1, 2, 3, 4, 5, 6. So we have a hexanoate, and it has a 2-methyl group. Do you see that CH3 sitting off there? So 2-methyl hexanoate. Okay, now I don't have a space in here because this is the entire carboxy side of the molecule. Over here, though, I've got a 2-methyl propyl. I'm going to keep that as a propyl group, not a propane or a propanoate, because that's on the alkyl side of the ester, the oxygen-bearing side. So this would be a 2-methyl propyl space 2-methyl hexanoate. So really the trick is just recognizing which side is the ester side and which side is the alkyl side, and then applying the rules accordingly. So we could have And here's the thing, we could introduce common names. So let's get this molecule from before was methyl on the alkyl side. It's got a CH3. Now this thing on the opposite side is formate because it's formyl derived. This one with a CH3 is an acetate because it's acetic acid derived. And this is a benzoate. So there's our common names from earlier. So we have acetate, formate, and benzoate we should be aware of. Okay, so we have methyl space formate. We have cyclohexyl, it's just a cyclohexane substituent, and then we have a space. And this is going to be acetate. Then we have ethyl space benzoate. So it's a little, I realize it's a little, it's probably a little annoying that the acetate and the formate don't follow that rule perfectly, but they're just so common. I wouldn't tell them to if they weren't so important. Like, for example, there are so many labs this semester where we used ethyl acetate as a solvent. That's a very common solvent. So I'm gonna just write that a little bit more legibly. Okay. All right, so that's ester naming. There's some common esters, kind of naming both sides. Abbreviated, we could have the abbreviated or truncated or shorthand structure. Okay, where we have R, CO2, R prime. Now the one that's closer to the carbonyl, that's our carboxy side. And the R prime is our alkyl side. That's the side that's closer to the oxygen. Just means very similar to the carboxylic acid shorthand. So if I had this molecule here, that would be benzene, carbonyl, O for the ester, attached to a methyl group. So that would be methyl benzoate, not the opposite. Not that structure. That structure would be MECO2. Just draw this bonded off the rest of the molecule, or you can put a pH there for phenyl. Okay, so I'll do it for nomenclature. Bit of a whirlwind, sure, but this is it for the nomenclature for the carboxylic acids and their derivatives. I don't really want to touch amides unless it's like a super important molecule. Same with acid chlorides, maybe like acetyl chloride would be it. And we've already seen oxalyl chloride, but those are the ones that are most productive for us to study. Okay, so I'll do it for this lecture on nomenclature. Everybody's favorite topic, right? Actually, carboxylic acid nomenclatures much more useful than some of the, as probably useful as like the fundamental alkyl naming, just because it's so prevalent in so many types of chemistries, whether that's traditional organic chemistry, biochemistry, or just pure biology, what have you. So anyway, that'll do it for this one. I'll see you next time.